Good morning, guys.
Morning, guys. Mrs. G here.
All right, Mr. Kane here. Today we're going to tackle some gas laws, the individuals.
All right.
We may handle 2, we may handle 4.
We did the legwork in the last video,
Yep.
especially with temperature.
We now know how to do pressure conversions
Yep.
and temperature conversions.
Yep. Now we're going to do the legwork.
All right.
Or was that the legwork? Oh, whatever.
All right. So we've got variables here for gas laws. It turns out that the things that you can change about a gas that will affect it are pressure, temperature, volume, and how many moles you got.
And notice the little note by temperature. Always, 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 always Kelvin.
Always in Kelvin, Mrs. G?
Always in Kelvin.
There's never a time where I don't do it in Kelvin.
Never. Always, always, always. 3 always.
Always, 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 always. All right, okay. I can handle that. All right. First law we got to talk about is Avogadro's law. I think I remember this guy, don't you?
I remember this guy, 6.02 times 10 to the 23rd.
Right, that's the same guy.
This guy?
Mm-hmm. He's the guy who came up with the idea that there are a certain number of particles in a mole. But he was talking about the fact that you can measure the amount of stuff, and he called it a mole.
Okay.
And he was talking about this with gases. He says that if you take a certain volume of a gas, it's going to have a certain number of moles.
Okay.
Right, so like 22.4 liters is going to be 1 mole. He then goes on to say that if you want to know how much 2 moles of a gas takes up, how much space it takes up, you could set up a proportionality.
Okay.
Okay, so V1 over N1 equals V2 over N2. So that way, if you had 1 mole that takes up 22.4 liters, then 2 moles would take up
44.8.
44.8. No calculator needed for that, right?
So he related volume to number of moles, which kind of makes sense if you think of a balloon blowing up. As you blow up a balloon, you are adding more particles of gas to the balloon, right?
Yeah, that makes sense, yeah.
And the balloon gets bigger.
And the balloon gets bigger as you do that. All right, so here's a little graph of it. So Avogadro's law states that the volume of a gas held at constant pressure and temperature varies proportionally with the number of moles.
Okay,
and
so
notice it's a direct relationship.
yeah, direct relationship. That's our balloon.
The more
example.
moles, the more volume.
Right. That
Right.
makes sense. And that's Avogadro's computation.
There's the computation. Yeah.
2 sets of conditions. Condition number 1 on the left, condition number 2 on the right. Put everything in the right spot. Are we going to have to use molar mass, Mr. Kane? Probably, right?
Probably,
Change
yeah.
it to moles.
Mm-hmm. It's possible that we might have a problem like that.
All right, so this chapter is going to be a lot of algebra, I get the feeling. Boyle's law. This is an Irish guy named Robert Boyle, and what he did was he found an opposite relationship to pressure and volume. He used a J-tube and basically changed the pressure and found that the volume...
How do you change the pressure?
Well, the story goes that he was living in a tenement somewhere and he ran up and down the tenement, but that sounds a little weird, but whatever it was, it might have been a mountaintop or something.
Like an apartment building? Like he ran up and down the stairs?
Us poor Irish people usually ended up in a 20-family tenement in the slums of New York.
Okay, so he ran up the tenement, and he found up higher in the tenement the air pressure should be lower.
Right.
So what did he find about the volume of the gas?
That the volume actually increased. So
lower pressure, the volume increases. Yeah. And so when he ran all the way down to the basement, there's more air pressure because there's more air. And
right. The volume decreased.
The volume decreased. Okay.
Yeah. So an increase of pressure is a decrease of volume.
That kind of makes sense because if you push more, if you push the particles together more in a smaller volume, they're going to hit the sides more.
Correct. It was the pressure he was playing with, and then the volume changed accordingly.
Oh, okay. That makes sense.
Yeah.
All right. So he found that this is what the graph should look like, right?
Correct. Opposite relationship.
This is an inverse graph, and so I see asymptotes. The volume, the pressure is going to continue to decrease, but it will never actually touch that axis.
Yeah. No.
And the same thing over here, there's an asymptote over here. It will continue to increase towards the y-axis but never actually touch.
This is the only relationship out of all the gas laws, this is the only one that has an opposite relationship.
Right.
All the rest of them are directly proportional. So this one should set in their heads.
And this one is the inverse relationship.
Correct. Right. This is the only one that has an inverse relationship.
So here's Chares' law. Chares was obviously a French scientist. And what he was playing around with he was playing around with volume and temperature.
Yep.
And you got a way to remember this, don't you? That it was volume and temperature?
There was a TV show called Charles in Charge. TV, Volume, temperature.
Volume. I
Yep.
see that. Okay.
Charles in charge.
So what Charles found out was that if you increase the temperature of a gas, its volume increases. This guy was a hot air balloon enthusiast.
Yeah, that's what hot air is.
That's what
a
hot
air balloon is.
Hot air expands.
Right.
Therefore, the volume gets bigger.
Correct.
When air gets colder, it shrinks down.
Correct.
Right. So
Direct relationship.
It's found using the mathematical equation V1 over T1 equals V2 over T2. It's a proportionality.
Yep.
Right? He finds that, again, it's proportional. So as volume goes up, temperature also goes up. Or the other way you could say it, as temperature goes up, the volume also goes up. Right?
As long as it's flexible volume like a balloon.
see.
So I noticed that with Boyle's law and Charles' law, here's the two gas laws we've done so far. Boyle's law was opposite. Charles' law was directly proportional. Oh, Avogadro, I forgot him. We did Avogadro. So we've done 3 gas laws. Mm-hmm. Of the 3 gas laws so far, 2 of them directly related, 1 of them opposite.
Right.
Of the 3 gas laws, 2 of the variables changing, 2 of them remaining constant.
Mm-hmm.
So the 2 that aren't in the computation are the ones remaining constant.
Yeah.
So this one would be pressure and number of moles.
Right.
Got it?
And that's because good science always has only 2 variables.
Yep.
Because on a graph, you can only graph.
The 4th and final gas law guy.
Gay-Lussac, French scientist. If you say it with an without the French accents, if you say it like an American would, people laugh at you.
I'm going to say, I call it Lussac's law.
All right, so Lussac's law. Gay-Lussac.
I'm an Irish woman from New York. I say Lussac.
I still got a little bit of French in me. So anyhow, Guy here, or Lussac, he studies pressure and temperature. So he's keeping number of moles and volume the same.
Correct.
And what he finds out that as you increase the temperature, you increase the pressure of a gas.
Which would make sense, because if you're lighting those poor little gas molecules on fire, what are they going to do? They're going to move faster.
They're going to move faster, and if they're going to move faster, you're going to hit the side of the container faster, and all those strikes against the side of the container mean more pressure.
More pressure, and as the pressure builds, ooh, you know what this reminds me of? Aerosol cans in an open fire pit.
You've done that?
Yep, that's what happens.
That's
why it blows up. It's not a flexible container.
Yeah, you're not.
So the volume stays constant. If you increase the temperature, the pressure is going to increase until it blows.
So that means that if I decrease the temperature, that means that the pressure will
go down.
Also go down inside the container. Okay, I think that makes sense. Is that why they actually say on aerosol cans that they have to be used and stored at certain temperatures?
Yeah. Don't put it in the oven. I don't know many people who put their hairspray in the oven anyway, so I guess we're okay.
All right, so here's the graph. Notice that as temperature increases, pressure increases. This is a direct relationship. Ms. G, do you want to review quickly the direct and indirects?
All right, we've had 4 laws: Avogadro, Boyle, Charles, Lussac's. 4 variables, 4 laws. Of all 4 laws, only one of them has an opposite relationship. That's Boyle's law. Pressure and volume are the only 2 variables that are opposite.
Okay.
Of the 4 laws, they're always studying 2 variables and holding the other 2 constant. All right.
Okay.
That's it then. We're going to do some demos in class.
So we're going to do some demos in class. We'll talk about each of the laws. You guys will have a little quiz here.
I'm not blowing up an aerosol can in class. That's a little dangerous, so that one might be something different.
How about a propane tank? You want to blow up a propane tank in class?
Let's go with a Coke can instead.